Welcome to lecture 13 of modern construction materials. We are going to talk about timber, wood and wood products, and we all know that timber has been used for a long time. Probably it was the first construction material used by human beings. Even today many people consider timber as the most sustainable construction material, as long as we can grow wood in the form of trees in forests, cut them down, replant and have the trees growing again, then it is certainly a sustainable material. All of us would certainly agree that wood is aesthetically appealing, easy to work with, and it has a lot of benefits in structural applications. What you see here on the screen are pictures of the Nagar castle near Manali in Himachal Pradesh. This is from the early 17th century. It's a beautiful building with very intricate carvings. The walls are made out of stone reinforced with timber, and many of the external structures, pillars and floors are made out of timber. As we know, wood is a naturally occurring biological material. It grows as trees, and as I said, it is probably the world's oldest structural material along with stone. Since it is easy to produce and handle, produce in the sense that the tree grows by itself with probably some help from us, it is easy to handle and therefore it is widely used as a construction material. The annual production of wood is tremendous, it is about 1 billion metric tons. So, lot of wood is used in one form or the other. For construction, we will see in the second half some applications, and also in furniture. Wood has good structural properties, it is aesthetically appealing and relatively cheap. Again, the cheapness or the cost depends on the type of wood and the durability of the wood. Though wood is vulnerable to fire and decay through biological attack, it can last for a very long time if properly maintained. That is, if it is coated and sealed, it can last for a very long time, and if the weather is such that there are not major changes in humidity and temperature, again it can last for a long time. Let us compare the properties of wood with some other materials. In this table, what we have done is looked at 4 different properties with reference to the density. So, the materials that are compared are wood, mild steel, aluminum alloys and concrete. In the first column, we have the Young's modulus divided by the density, or the elastic modulus normalized with the density, and you find that wood has a value of 20 to 30, same range as mild steel and aluminum, and better than concrete, which is obviously much heavier. In terms of the tensile strength, again divided by the density or relative to the density, we have wood having values of 120 to 170, much better than mild steel and comparable to aluminum alloys, and much better than concrete, which is very weak in tension and also has a high density. In terms of the compressive strength, again wood has good values 60 to 90, which is comparable to aluminum and much better than concrete. Fracture toughness K1C divided by rho, the density, again in wood you have a wide range from 1 to 12, which is comparable to the metals and much better than concrete, which is a brittle material and a heavier material. So, we find that in terms of unit weight, in terms of properties with respect to the unit weight, wood comes out very strongly compared to other materials, and therefore it is a structural material that has been used for a long time and will continue to be used as long as it is available. Wood, however, is more complex than many other materials, because first of all it is a natural material. There are at least 30,000 species of trees, and many of these are used as to give us construction materials, and this variability between the species alone leads to a tremendous variation in the properties of wood. So depending on the species of tree, we can have very different properties, and that is why we have certain types of wood which are more common in construction or more ideal for construction. Wood is a composite material where we have a variety of properties at different scales, and therefore the analysis and the modeling is to a certain extent complex. Being a natural material, it can have a lot of flaws and imperfections, which again can control the structural behavior. Lastly, an aspect which makes wood again very different from other materials is that it is anisotropic because of the way the tree grows. Trees are divided into two broad classes: hardwoods, which are basically tropical broadleaf deciduous trees, and these have some porosity, they have vessel elements in the wood. Examples are teak, sal and oak. Softwoods are conifers, they have needle or scale like evergreen leaves, and they are generally non porous. Examples are fir, pine and cedar. The fact that some are called hardwoods and some are called softwoods does not mean that the hardness of the wood actually changes. It is just a nomenclature to divide the woods according to how they grow and what they look like. Some common Indian species are given here: teak, which is a very popular wood which has an appealing brown color. It has good dimensional stability and natural durability, it is not attacked by termites very often, and it does not change dimensions when temperature and humidity change. The heartwood, that is the interior part of the wood, varies from yellow brown to dark golden brown. Then there is a wood called paddock, which is more red orange in color. This is a medium density hardwood, and in some cases now we are finding lot of applications of rubber wood, which is a light hardwood, and it after seasoning it becomes lighter in color. So I have put some of the images of the wood here to see that we have a range of colors which gives different aesthetic appeal, and when you have a clear coating on the wood, the color and the grains are brought out. Here what the design that you see comes from the grains that make up the wood structure. There are other common species of trees that are used in construction in India. For example, sal, which is strong hardwood, dark brown in color; deodar, a light durable wood, light brown in color; and a wood that is used a lot in furniture because it is very expensive to be used in construction is rosewood. It is a heavy wood with high strength. The heartwood varies in color from golden brown to dark purplish brown with blackish streaks. So these and many other types of wood are used in India for construction. Now in order to understand why we have the anisotropy and the variability in the properties of wood, we have to understand how the tree grows. Now all of us have seen trees, and basically you have a crown, the visible part above the soil, and which is held up with a trunk, which is where most of the wood that we used in construction comes from. At the base you have an enlargement, there is a buttressed base, and in the soil we have a system of roots a tap root and several roots at the side, giving us the lateral root system which holds up the tree, sucks up the water, and the capillaries take the water and sap up the tree to help the tree grow. Now if we were to take a piece of wood from the trunk and look at it closely, you would see something like this. You would see in the interior the pith, then you have the hardwood, which is harder wood that is not living anymore. Then we have the sap wood, where the sap is being transported up the tree, and when you look at the cross section you will see a lot of rings. Each ring represents 1 year of growth. The spring wood is lighter and larger width compared to the summer wood. On the outside we have the cambium, which is the growing layer, and on the very outside you have the bark of the tree. The direction of the growth of the tree is the axial direction or the grain direction. This is where the fibers, most of the fibers will be aligned here. There are some cells which are also leading to lateral rays forming, that you see here, but most of the grains are running along the axial direction. Perpendicular to that we have the tangential direction, tangential to the circumference of the tree, and then the other direction is the radial direction. These are the three principal directions of the properties of wood: the axial direction, the tangential direction, and the radial direction, and all of these are in reference to the growth of the tree, because the direction of the growth of the tree or the longitudinal direction is where we have the best properties, because the fibers run along that direction. So on the macroscopic level we can identify the outer bark, which is a rough layer of protection for the inside of the tree. The inner bark transports the saps from the leaves to the growing parts of the tree. The cambium is a layer of tissue about 1 to 10 cells thick between the bark and the wood. The sap wood is the wood on the outside, which conducts moisture from the roots and stores food. The heartwood is the inner core, which is non-living. It is harder, more resistant to decay and drier. Then we have a small amount of cells called rays that grow in the horizontal direction. So this is basically what we observe in the macroscopic level, and this gives us the different properties and the directionality of the properties, as we will see later. So again we have now a section of a tree trunk. We have the outer bark, the inner bark, and the cambium that makes up the outermost layers. Then we have the sapwood, which is where the moisture is running, and then we have the heartwood, which is drier and harder. Right in the middle we have the pith, and we have rays which can be running across, and then you have these giving us these lines, and each ring tells us how the growth occurred during 1 year. The annual rings are what gives the most distinct feature of the tree trunk. It also gives a certain design and aesthetic appeal when it is cut across a ring, when the wood is cut across a ring. As the cells of the cambium grow and divide during the growing season, they form these ring of cells around the trunk. In spring, where there is more water, rapid growth, these cells that of the cambium have larger dimensions with thin walls, and this is called the spring wood or early wood. Later, when there is less water, the cells are smaller with thicker walls and therefore end up being harder and stronger. This is called summer wood and late wood. And since there are these differences which occur over a year, we have a distinct look or the annual rings which can be distinguishable in the cross section of a tree. Other than this, we have what are called knots. Knots are where a branch grows out of a trunk. You can have a green knot where there is a good integration of the knot with the rest of the wood, that there is no weak interface between this part where the branch grew from and the trunk. Or sometimes what happens when the branch grows, part of the bark of the branch is embedded in the wood of the trunk, and this gives us now a weak interface which is called a black or dead knot. And when a plank is cut, this part can come out very easily because it is not bonded, it is not integral with the rest of the wood. So a green or live knot occurs if the cambium of the branch is still alive when it fuses with that of the trunk and there is continuity in growth. If the cambium of the branch is dead, there is absence of continuity and the trunk grows around the dead branch and even the bark, and therefore you get a black or dead knot. And as I said before, these knots may drop out of the plank on sawing or later, and this has to be avoided. When we look at the microstructure, wood is made up of cells, and wood can be modeled approximately in a general sense or crudely as a bundle of aligned tubular cellulose cells or fibers. You can imagine a bunch of straws, like hollow straws, making up the wood structure. The middle lamella bonds the neighboring cells. So, the cells are held together by the middle lamella. The cell itself has two walls. The primary wall is thin with randomly oriented microfibrils. Microfibrils are bunches of aligned fibers or cellulose cells. What did I say? I said something wrong, right? Let me start this thing again. So, wood is made up of cells that are bundled together, and therefore it can be modeled approximately or crudely as a bundle of aligned tubular cellulose cells or fibers glued together. You can imagine it as a bunch of straws glued together, making up the structure of wood. The middle lamella bonds the neighboring cells, that the cells are bonded to each other by this middle lamella. The cell itself has two walls. The primary wall of the cell is thin with randomly oriented microfibrils. Microfibrils are bunches of polymers that are held together. The secondary wall of the cell has three layers: a thin outer layer, a thick middle layer, and a thin inner layer. And these layers have microfibrils oriented in different directions. Microfibrils again are bunches of polymer chains. And here you see this better. So, each of these boxes is a cell. The middle lamella is what bonds one cell to the other. The cell itself has a primary wall with randomly oriented microfibrils, and then we have three layers in the secondary wall: the middle layer, the outer layer, and the inner layer. The middle layer is thicker than the inner and the outer layers, and these have fibers in different directions. So, this makes up the basic cell unit which gives us the properties of the timber. Now at the bottom right we see a transmission electron micrograph of a cell wall. This is the middle lamella, this is now the cell wall. We have the primary layer on the outside, and then we have the outer layer, the thick middle layer, and a thin inner layer. Now what makes up the cells, or what are the different types of cells inside wood? In softwoods, 90% of the volume of the wood consists of longitudinally oriented cells called tracheids. These are along the axis of the tree. Then there are a few transversely oriented cells called parenchyma. So these are perpendicular to the direction of growth of the tree. In hardwoods we have more, other than these two we have other aspects also. The microstructure is more complex. They have the tracheids and the parenchyma, the hardwoods, but in addition they also have fibers and pores. So this would be how a tracheid looks like. So these are the cells in the early wood. They would be larger and with thinner walls, and in the late wood they are more slender and harder, and inside you see how the early wood tracheid cell walls look like. So they are like these hollow tubes which are making up the cells. The microstructure can be visualized this way. These are some 3D images of wood blocks. Say in a softwood we have the tracheids and some parenchyma running in the other direction. In a hardwood, in addition to this we have some fibers and we have voids also in hardwoods. These are the different types of cells found in the softwoods and hardwoods. In the softwoods we have the tracheids and the parenchyma. In the hardwoods, in addition to these two, we have fibers and pores or conduction vessels. The function of each is given here. The parenchyma basically work for storage, the tracheids for conduction of sap and moisture and also for support, the fibers basically for support, and we have these large vessels or pores for conduction. These are relatively how the shapes and the dimensions look like. The length of the parenchyma is very small, about 200 microns. The others are in the order of millimeter to a couple of millimeters in length. The width, the parenchyma, tracheids and fibers are in the order of about 20-30 microns. The vessels are wider, ranging to about 500 microns. So these are the different cells that are found inside the timber. What makes up these cells? All wood is composed of cellulose, lignin, hemicelluloses and minor amounts of other materials, extraneous materials in the cellular structure. Variations in the characteristic and volume of these components and differences in how they are put together in the cellular structure makes the wood either heavy or light, either stiff or flexible, either hard or soft. So all wood has the same microstructural materials which build up the wood. The way they are put together and the relative proportions give us the different properties of the wood. Cellulose is the major component. It constitutes approximately 50% of the wood by weight, that is half the wood weight comes from cellulose, and this is a high molecular weight linear polymer built from the glucose monomers. And when something is a linear polymer, you remember that you can have some amount of crystallinity that there is a arrangement possibility of having these molecules arranged. So during growth the cellulose molecules arrange into strands called fibrils, and these molecules are bonded together by a combination of hydrogen and van der Waals bonds, making up the cell walls of the wood fibers. So most of the cell wall cellulose is crystalline, that is there is an orderly arrangement, but some part is non crystalline, but most of it happens to be crystalline. Lignin is the gluing material that binds the cells together. Lignin constitutes 23 to 33% of softwood, 16 to 25% of hardwood, and as I said, it is the cementing agent that bonds the cells together. Lignin is a 3-dimensional phenyl propanone polymer. We also have hemicelluloses, which are branched low molecular weight polymers, and we can have low quantities of extraneous materials like oils, resins, fats, calcium, potassium and magnesium. So this is the relation between what happens in the nanoscale and what happens in the microscale. We have a tracheids here, say a softwood cell few millimeters long, and if you look at the cross section you would see the cell wall, the outside is the primary layer, and then we have the secondary wall with 3 different layers, and within the layer you have these cellulose chains bonded together as microfibrils. Most of the region is crystalline, you can have lengths of about 30 to 60 nanometers of crystalline regions, then small non crystallinity comes in where there is a disorder, and this together makes up the microfibrils, again a few nanometers in width. So this builds up into giving us the cell wall. Now if we were to take a section, a longitudinal section which looked like this, where you have the chains of cellulose, a cross section again shows us these molecules of cellulose which make up the microfibrils. So in a very basic level we have polymer behavior which leads on to the behavior that we see in terms of the properties of wood. So we saw that wood is orthotropic in nature, that is along the direction of growth it will have different properties than in the radial and tangential directions. This is because of the way the tree grows. There are therefore now 9 independent constants that are needed to describe the elastic behavior of wood. In an isotropic elastic material we would just need 2 constants, the Young's modulus and the Poisson ratio, but here because you have the directionality, because you have the orthotropy, and the behavior is different in the longitudinal direction, radial direction and the tangential direction, we need now different elastic properties depending on which direction we are considering. Again to remind you, the longitudinal direction is the fiber direction, or what is also called the grain direction, and this is the direction that the tree trunk grew. Now depending on how the log is sawed, how the boards are made and planks are made, where you have a quarter sawn board that is from the middle almost along the diameter, or a plain sawn board which is at the other end near the outside of the tree cut across like this, you can have the grains oriented in different ways. This affects the properties and also the look that we have in the wood. So the way of sawing affects the properties of the timber as well as the decorative features. Let us start looking at some of the properties of wood. The specific gravity is a very important property because we find that many of the engineering properties are related to specific gravity or the relative density. For all species of wood, the specific gravity of the cell wall material itself is about 1.5. This does not vary from one type of tree to the other. The specific gravity of the cell wall itself is always about 1.5. However, there is a lot of void space and porosity which changes the specific gravity of the wood from 0.04, which is the case of balsa wood, which is very light, to something that is denser, to about 1.4 for a species of tree called Lignum vitae. And as I said, there are these differences which come between the species due to the variations in the void space and porosity within the geometry of the wood cells and their grouping. Remember, we had talked about the differences between the softwood and the hardwoods. So there are lot of variations in how the cells are put together and the type of cells and their relative proportions in the wood, which give rise to different specific gravities in the wood. Specific gravity, as I said before, is a good indication of the mechanical properties. Within the same species, mechanical properties vary linearly with specific gravity. That is, if you take teak wood, a particular teak wood with a higher density, higher specific gravity will have better mechanical properties than another teak wood with a lower specific gravity. That is what this means. Other than the mechanical properties, another indication or another aspect of specific gravity, or other than the mechanical properties, another significance of the specific gravity is that lower specific gravity gives more ease for cutting the wood with a sharp tool. So suppose engraving has to be done, sculpturing has to be done, intricate elements have to be made out of wood, then it is better to use wood with a lower specific gravity, because you have less density and it is easier to shape the wood. However, for structural purposes, we want better mechanical properties, and therefore we go with a wood of higher specific gravity. In terms of moisture content, it is very important to understand the different effects. Initially, as soon as a tree is cut, the moisture content of green wood, that is fresh wood, is very high. It can range from 60 to 200% depending on the type of wood and how it is grown. So there is a lot of moisture in the wood. Green timber, that is freshly cut timber, will yield moisture to the environment, that is, it will lose moisture to the environment because the environment is generally drier than the timber itself. Consequently, it shrinks, that is, it changes its dimensions. So obviously we cannot use fresh timber in a structural element and allow it to lose moisture and change its dimensions. Later on we see that this is the reason why we season timber and we reduce the moisture that is there. For every combination of relative humidity and temperature of the environment, there is an equilibrium moisture content of the wood. That is, that if the wood is left in an environment for a long time, it will reach a certain moisture content that is in equilibrium with its environment. That is, it will not continue to decrease or increase much more as long as the environment does not change. However, there are a lot of environments which do change. You have a wet season, you have a dry season, and again we cannot allow the moisture content of the wood to vary a lot. So that is why we have to seal wood, we have to protect the wood from losing or gaining moisture after it is being put into place in a structure. However, initially we would like the wood to lose moisture such that it does not shrink or change dimensions later. Also we will see in a minute that the moisture content also is related to the strength and other properties. Lower the moisture content, better are the properties, and therefore we would like the moisture content to be lower. Another important fact regarding moisture content is moist wood is more susceptible to attack by fungus. So, fungi can attack wood which is in wet conditions and moist. That is another reason why we do not use green timber as such. We allow the timber to dry. We would like the timber to be drier when we are using it in a structure, and we seal it such that it does not gain moisture from the outside, and we do not allow the wood to be wet often. So, for all these reasons we want timber to be dried before its usage. The process of drying the timber is called seasoning, where there is controlled drying done to remove the sap, reduce the moisture without causing cracks and distortion, because if there is sudden drying, if we were to do this drying very quickly, the process of removal of the moisture will cause cracks and a lot of distortion. Natural or air seasoning takes about 2 to 6 months. It is faster if it is immersed in water before drying, because all the sap comes out into the water and drying is faster. This is what was traditionally done, but there can be artificial means of seasoning by using kilns, boiling, using chemicals for the seasoning, and even electrical seasoning to create heat within the wood to drive off the moisture. So, seasoning is something that is very important, and for construction purposes, even for making furniture, we always use properly seasoned timber. So, what happens during this drying? Moisture in wood exists in two forms: free water within the cell cavities in the hollow parts of the cell, and bound water which is adsorbed in the cell walls. So, there is some water in the cell walls bound to the polymer molecules. As the green wood dries, as the freshly cut wood is seasoned and allowed to dry, first the free water evaporates, that is the water that is not bound, which is within the cell cavities, comes out first, and we reach a certain point called the fiber saturation point, where all the free water has been removed, but the cell walls are still saturated. We have removed all the water from the interior of the cells, but the walls themselves are still saturated with water. This generally occurs at moisture contents of about 25 to 30%, that is called the fiber saturation point. Until that point in time, the properties do not change much and there is not much shrinkage when you are removing the free water. If we continue to remove water, further removal of moisture compacts the molecular structure, leading to better hydrogen bonding. So, the molecular chains now are free of water that is separating the molecules, they come closer together and the hydrogen bond becomes stronger. Consequently, the wood shrinks and becomes stronger, the properties become better. This process is, however, reversible. This is very important to remember, that we should protect the wood such that water does not enter into the wood, because again what will happen is the wood will swell and it will become weaker. So, we have to protect the seasoned wood such that water does not enter. In all environments which are prone to major changes of moisture in the air, wood should be well protected. Only in cold, dry environments we can expose wood. This happens, say, in the north of India. You can have some places where wood need not be protected and still can last for a long time, but in most other parts we have to protect wood so that there is no entry of moisture after seasoning of the wood, which can lead to swelling and weakening of the wood. So, this graph tells us what we discussed in the previous slide, where we have on the x axis the moisture content of wood, and on the y axis we have the maximum compressive stress or the compressive strength of wood. And as we remove moisture, say we have a green wood with about 100 or 120% moisture content. We start removing the water, we remove the moisture, and now we are first removing the free water. So, we remove the free water, the strength does not change much with this change of free water content. Then we reach the fiber saturation moisture content, fiber saturation point, and if we continue to decrease moisture even beyond this, now this is about 25 to 30%, then we find that now the cell walls are drying, there is compaction of the cell walls, the molecular chains are coming closer together, there is better hydrogen bonding, and therefore the material strength increases. So, if we decrease the moisture content much below the fiber saturation point, we have an increase in strength, and this is what we want. So, this is what we want to achieve by proper seasoning, and this we find in many other properties also. This is a graph from the USDA document where we have different properties such as tensile strength parallel to the grain, bending strength or modulus of rupture, compression parallel to the grain, compression perpendicular to the grain, tension perpendicular to the grain. We find that in all the cases we have a decrease in the property as the moisture content increases. So, during seasoning we first remove the free water, and then as further moisture is removed we have an increase in the strength. Only in the case of the tensile strength parallel to the grain we have a reversal here. When the material becomes very dry, it becomes brittle, and you can have tensile failure at very low moisture contents, but otherwise always you have a trend like this, where as we remove water, until the free water is removed there is no change in the property, and afterwards as we remove the cell water or the bound water, the property becomes much better. So, this is what we achieve during seasoning. Along with the removal of moisture content, we experience a dimensional change in wood, or along with the reduction of moisture content, the wood experiences a dimensional change or shrinkage. So, when we change the moisture content, when there are changes in moisture content above the fiber saturation point, the dimensional stability does not change, but below the fiber saturation point, if the moisture content now is lowered below the fiber saturation point, there is volumetric shrinkage of wood, which is approximately proportional to the volume of water removed. So, the wood shrinks proportional to the volume of water that it loses. Shrinkage is however not the same in all directions. We find that in the longitudinal direction it will be the least, and it will be more in the other directions. And this shrinkage is important because during seasoning of a timber piece, since we have differences in the shrinkage in the three directions of wood, we will have distortion or warping of the element. So, we can have flat, square and round pieces, and this diagram shows you depending on where it has been cut out of, it can warp, or it can have more uniform decrease of volume, or a circle can become like an ellipse. So, depending on where in the log the plank is cut or the piece is cut, you can have non-uniform change in volume or non-uniform change in the dimensions, and this has to be kept in mind when we cut a log into pieces. The tangential direction, we have shrinkage that is almost equal to that in the radial direction, and both of these are much higher than the shrinkage in the longitudinal direction, that is along the direction of the growth of the tree. So if we look at values, as I said, the longitudinal shrinkage is very small, it is normally negligible. However, the tangential and the radial shrinkage values, these are strains, can be, however the values of the tangential and radial shrinkage can be in the range of 3 to 12%, the tangential shrinkage being higher than the radial shrinkage. Some values for teak, radial shrinkage can be about 3%, tangential shrinkage can be 6%, and overall volumetric shrinkage can be about 7%. The shrinkage in the longitudinal direction is almost nothing for teak wood. So this again shows you how shrinkage occurs as a function of the moisture content. On the y axis we have the moisture content as percentage in wood, and on the x axis is the shrinkage. So we find that as the moisture content decreases, that is we are drying the wood, we can have shrinkage in the tangential direction which is quite high, followed by the radial direction, shrinkage in the radial direction. In the longitudinal direction, shrinkage is very low. So this is the amount of shrinkage as a function of moisture content, and as we are seasoning or the wood is drying, the moisture content is dropping and the wood experiences shrinkage or an increase in shrinkage as the moisture content drops. And what we see is that in the longitudinal direction, along the grains, along the fibers, shrinkage is very low, but in the other directions you can have significant shrinkage, and this should be kept into account when we are looking at the dimensions. And also, to reiterate, it is very important to seal the wood and protect moisture from coming in once you are using the wood in the structure, because this can lead to swelling and distortion of the structural element. So we have looked at the microstructure of wood, we have seen why there is a lot of variation and anisotropy in wood. In the second part of this lecture, we look more at the properties, the different properties, we look at typical values, and we look at applications of timber, and we will end up also talking about composites that can be made out of pieces of wood or particles of wood. Thank you.